Hi, my name is Adam Lekowitz. I'm a PhD student at UMass Amherst. I'm presenting our paper on learning augmented competitive algorithms for spatiotemporal online allocation with deadline constraints. This is a new problem that we propose and study. This is joint work with Nico Christensen and Adam Weirman at Caltech, Bo Soon at Waterloo, Naman Bashir at MIT, and my advisors, Mohammed Hajismaili and Prashant Chenoy. So I'll jump right in and talk about the motivation for the problem. In recent years, there's been lots of work towards reducing the operational carbon footprint of data centers. One problem in this area is, suppose I give you a batch job with a certain deadline, and you have access to some globally distributed data centers. Then your goal is to schedule and migrate this job in order to reduce the total carbon footprint while still respecting the deadline. And within that task, what I'd like to motivate is that there's an interesting online optimization problem. The first dynamic of the problem is that we'd like to ultimately reduce some costs, for example, the carbon footprint of earning the job, and these costs are both time varying and uncertain. Since the job is interruptible, our schedule may incur some extra overhead due to loading things in and out of memory. I mentioned that, multiple data centers can work on this job. For example, maybe this is running on AWS and you have the option to migrate the job between regions, but that also comes with some overhead. And finally, the deadline imposes some long-term constraint. So over multiple time steps, there's something concrete we have to accomplish. So we're motivated by this application, but ultimately the message of our work is that we can formulate and solve an online optimization problem that captures all four of these components. We call this problem spatiotemporal online allocation with deadline constraints, or SOAD for short. The decision maker or player in the problem makes decisions in a metric space with endpoints. In the motivating example, these might be our data centers. At a single step, they choose a point in the metric, and then at that point, they can fractionally allocate some resources to the workload. We represent those allocations using two states, on and off. In SOAD, we model the deadline constraint as a function that maps a player's decisions x to a certain amount of progress in the constraint, and we assume this function is known to the player. We define it as a linear function of the on allocations. So CU here is a constant that describes the marginal throughput at point U, and we will require that the sum of this function applied to all of the player's decisions satisfies that deadline, finishing the job. Subject to that constraint, the player's objective is to minimize three sources of cost. The service costs are revealed online, and they are also linear functions of the allocations. So f sub tu gives the service cost of point U at time t. We place one assumption on these, namely that there are known upper and lower bounds. The player pays a movement cost defined by the metric, given by this distance function d, and if the player changes the amount of resources assigned to the job at a single point, they pay some relatively smaller switching cost to do so. We assume that there is a known constant upper bound on the switching cost given by tau, and d corresponds to the largest distance between 2 points in the metric, which implicitly assumes the metric is finite. To analyze our algorithms, we use the classic notion of competitive analysis, which seeks to get the best guarantee on this algo-over-opt ratio over all instances. Now, in the online algorithms literature, the simultaneous components of SOAD have not yet been studied, although there's two tracks of problems that are sort of adjacent. The first of these is metrical task systems, where SOAD adds this notion of a long-term constraint, that we have to complete some overarching goal over multiple time steps. And then the other we classify as online search, and SOAD adds the notions of movement costs, switching costs, and multidimensionality when compared against a general online search problem, such as one-way trading. Between these two tracks, we see quite distinct techniques, so being able to bridge the gap is really an open problem. And with SOAD, the approach we took really draws on techniques from both of these literatures to make the problem tractable. In the full paper, we design a competitive algorithm and a learning augmented algorithm to solve this problem. Here, I'll just give a flavor of our main results. First, we have a classic competitive algorithm called PCM. We show PCM is log n eta competitive, where eta is given by this expression, and we also show that eta is the best achievable competitive ratio. So PCM is optimal up to log factors. The W here is indicating the Lambert W function, which you can kind of think of as log. Intuitively, we see a lot of the SOAD parameters like U, L, tau, and D in this bound. We also design a learning augmented algorithm called stclip. This algorithm uses machine learned advice of the best decisions at each time step to improve its performance. We prove a 1 plus epsilon consistency for any given epsilon, where consistency means how well we match the optimal performance when the advice is correct. And for a given epsilon, we also prove log n gamma epsilon robustness, where robustness is the classic competitive performance of the algorithm given bad advice. Gamma epsilon is given by the solution to this transcendental, and we also have a lower bound that states any 1 plus epsilon consistent algorithm is at best gamma epsilon robust. So we're again optimal up to log factors. To summarize things, we have introduced and studied SOAD, motivated by emerging problems in areas such as sustainable data centers. We designed a competitive algorithm and a learning augmented algorithm, stclip, for the problem, showing that they are all optimal up to log factors. In the full paper, we also implement and validate these algorithms in a sample application to carbon-aware workload management. Thanks for listening to this quick talk. Our code is available on GitHub, and my contact information is listed on the slide.